Today we are gonna go through surface water. This is the last chapter of hydrologic processes. Then after that we are gonna go through the statistical approach on hydrologic events. Subsection of surface water is sources of stream flow. We need to cover what is the sources of stream flow. First of all, let's define the watershed, which is catchment, is the area of land draining into a stream at a given location. The surface water processes vary through time during a storm. Here, storm is defined as like precipitation, the rain events and stuff. Assume continuous and constant precipitation. Precipitation contributes to various storage and flow processes is shown in following figure. Here we can observe when the precipitation occurs, there is a time since precipitation began, the time period versus the rate relative to precipitation rate. Then we can observe there is an overland flow, unsaturated flow, groundwater flow, and soil moisture, surface storage, and infiltration stuff. The rate of all these is given, also the channel flow is given. In the shaded area is detention and gray area is retention. So let's define all this stuff and then let's go back to this figure and we can understand better what we mean by drawing these rates. Retention is storage held for a long period of time and depleted by evaporation. And detention is storage held for a short time period and depleted flow away. So retention is like, we can think as like soil moisture which is kept with the soil for a long time period, and detention we can consider as like a ponding of water, and then it's gonna just flow away during the time, short time. When flow away due to the detention occurs, we have three flows: unsaturated flow, groundwater flow, and overland flow. Unsaturated flow is like a subsurface flow. Groundwater flow is like saturated and then it's in the below unsaturated zone. And overland flow is on the top of the surface like a ponding, and we can consider like this one later on as a surface flow, and we can divide it into categories. And we also have channel flow. This is the main form of surface water flow. The precipitation which becomes stream flow may reach the stream by overland flow, subsurface flow, or both. Okay, after we define detention and retention, like let's remember, this is for long time period, this is for short time period of rain like ponding and soil moisture. So we can see the rate relative to precipitation rates and time since precipitation began. We have channel flow, this is like a surface flow, right? And then we have overland flow, unsaturated flow, groundwater flow. These guys is like subsurface flows. This one is subsurface flow. This is called like groundwater flow. It's already defined. This guys is surface flows. Okay. And as you see, the rate of relative rate for the precipitation, the surface flow is higher than the other stuff. We have here, we can see the gray stuff is a detention, which is like above the soil moisture. As you see, this is a soil moisture line. Above it is like a ponding, the water is just flow away. Here the shaded gray is like a soil moisture below it, so it's detention is called detention over here. Alright, so when we see this one, we can understand how it's our source of stream flow behaves accordingly. Now let's define type of stream flow. We have Hortonian overland flow, which is neglecting vegetation and assuming the intensity of rain minus the infiltration is the rainfall exceeds. So this is called like how much precipitation comes minus the infiltration rate. Like when we subtract each other, this is the rate of flow on the overland. And we have subsurface flow, which is vegetated surfaces in humid regions. It's occurred in vegetated surfaces in humid regions. And we have saturated overland flow. It means the subsurface is saturated and then the top is ready to flow. Here is soil is saturated by subsurface water, so the saturated overland flow occurs. The other sub-chapter is in surface water is stream flow hydrograph. A stream flow or discharge hydrograph is a graph or table showing the flow rate as a function of time at a given location on the stream. There are two types of hydrographs are important. One of them is annual hydrograph, the other one is storm hydrograph. Let's define all these both hydrograph. First one is annual hydrograph. The annual hydrograph, a plot of stream flow versus time over a year, shows the long-term balance of precipitation, evaporation, and stream flow in a watershed. There are these three common examples are shown on the figures, and as you see on the land on the left side of the figure is there is an like by the time, like by the months, there are like spikes when there is like a storm occurs, it shows. Okay, then there is a dry land, there is no discharge on January, February, then it start to rain or precipitation, it directly jump, then decrease to the dry land again, and then increase and decrease. And there is also the third one on the right hand side is very smooth. It's just like occur in May, June, July, August. It's like a monsoon rain time. Okay, on the left hand side it's frequently occurs the storm. When the precipitation comes, the intensity is high, like it's kind of like arid regions or like semi-arid regions. But in the middle is like dry, like a desert area, like it comes directly. The storm is coming very high, and then it fades away, it's jumping, like the elevation of the discharge is high. And the other one is like an is kind of like smooth. There is always raining seasons, but the intensity is high, a little bit high, like May, June, July, August. Maybe it's like a rainforest or something like that. But we mostly concentrate on storm hydrograph. Annual hydrograph shows that the peak stream flows are infrequently appears. It's the result of storm rainfall or storm rainfall or snow melt combined. So here we have an example of storm hydrograph. We have flow rate versus time, and as you see, from A to B is called base flow recession, and point B to C is rising limb, and C to D is falling limb, and D to E is base flow recession again. B to C, there is an the intensity of the flow rate is getting higher, that's why it's rising, and then when this, like, let's say precipitation is done, then it start to decrease the flow rate, so that's why it's calling falling rate. After we define all the surface water definitions, let's go through the calculation stuff. We have two main parameters. One of them is excess rainfall and other one is direct runoff. Excess rainfall, which is also called effective rainfall, is that rainfall which is neither retained on the land surface nor infiltrated into the soil. After flowing across the watershed surface, excess rainfall becomes direct runoff at the watershed outlet under the assumption of Hortonian overland flow, which is there is no vegetation. It was assumed there is no vegetation to take in infiltration, right? Increase the infiltration rate. Excess rainfall hydrograph, which is synonym of ERH, is a key component of the study of rainfall runoff relationship. The difference between the observed total rainfall hydrograph and excess rainfall hydrograph is termed obstructions, which is also known losses. Obstructions are primarily water absorbed by infiltration with some allowance for interception and surface stores. That means losses are primarily water absorbed by infiltration. In order to determine obstruction, phi index is used. This phi index is that constant rate of obstructions that will yield an excess rainfall hydrograph with a total depth equal to the depth of direct runoff, which is represented by R subscript D over the watershed, which is catchment. So RD is equal to the total of M1 to capital M, parentheses RM minus phi delta T. So phi index, we are gonna find it. Rm is the observed rainfall in time interval M. Delta T is the time period. So let's solve one example and then we can understand better how can we define, how can we calculate the direct runoff depth. In this example, determine the direct runoff hydrograph, the phi index and the excess rainfall hydrograph from the observed rainfall and stream flow data given in table. The watershed area is 7.03 miles square. So in the table I'm giving here, we have time period and we have observed rainfall and stream flow. Alright, we have this table. Let's write it down on Excel. Let's try to solve on Excel. Time. We have 8:39, right? So till 4:30, which is 8:16:30. All right, and we have let's say observed rainfall here. rainfall, observed rainfall, and stream flow. Okay. Till 9, right? Till 9 is 0.15, 0.26, 1.33, 2.2, 2.08, 0.2, 0.09 till 12 a.m. Inch of rainfall occurs, and the stream flow is 203, 246, 283, 8, 12, 23, 23, 5, 6, 9, 7, 9, 5, 2, 1, 11, 0, 25, 8, 2, 2, 1, 2, 2, 4, 6, 1, 8, 0, 2, 1, 2, 3, 0, 7, 1, 3, 3, 9, 4, 3, 8, 3, 5, 4, 0, 3. Okay. And cubic feet second of stream flow occurs. All right. Okay. We write it down these terms, and we are gonna calculate it. Our base flow. Before we go through base flow, we need to know like how this trend or like a storm hydrograph behave. Let's try to sketch this graph on Excel. Here, let's try this guy. Yeah, okay. As you see, this is a storm hydrograph, and as you see over here, there is an base flow, like let's say is like you see is coming straight, and after that it goes up. Let's see what is the number of this guy. 394. Let's define it like in the book also given like a 400 cubic feet cube. Let's say this is base flow, and either you can put 394 or 400, let's say, or 394 or say 400. Okay, 400 till down, and then let's add here to see how the base flow is shown on our graph. As you see, is a fixed base flow on the red light. Then the up is our stream flow, like limb and rising limb and falling limb. All right. So if we know that 400 cubic feet second is our base flow, then we can see that as after 400, which is here, the direct runoff is gonna start to occur. So let's say direct runoff hydrograph. If first of all, let's say our time interval is from here 1 till here, which is below 400, so there is no direct runoff. So 1, 2, and then let's do this guy, and then let's scroll down till here. So 11, half an hour of 11, right? 11 numbers of time duration. And let's calculate our direct runoff hydrograph from here where it occurs is equal to stream flow minus base flow. Then we need to scroll down and we can calculate it here. Then we can stop over here to calculate our excess rainfall hydrograph parameter in order to find what is this rainfall occurs. Okay, so let's first of all try to find the depth of the direct runoff. In order to do this one, we need to see how much runoff accumulated this on the top of this stream flow storm hydrograph. So the mine is Turkish, so you guys can see on your Excel is a summation from here to here. So it's 43,550 cubic feet second of water accumulated on this storm hydrograph. Let's stop over here and then start to solve on our paper. Okay, first of all, we need to find the volume of direct runoff depth. The direct runoff. So in order to do this one, we need to use this formula, right? So where the volume of direct runoff is m is equal to 1 to the event is 11 interval, the qn, which is the stream flow, multiply delta t. And if we see these guys, if we plug all these parameters, we can get is equal to 43,550 cubic feet second, right? Cubic feet per second, multiply 0.5 hours of volume of water. When we take the unit conversion as like here, let me make it a little bit bigger. So 43,500 feet cube over second, 0.5 hours, which is hour. We need to convert it to second in order to cancel these guys. So we need to multiply by 3,600, and the result is gonna be 7.839 multiply 10 to power 7 feet cube of water volume is accumulated on this storm hydrograph. Then in order to find the depth of direct runoff, what we need to use, we know the catchment area or watershed area. So we need to divide this volume of water into the area in order to find the depth of this direct runoff. So we just need to add this, where is it? Here, the VD, and we know that the area of this watershed is 7.3 miles. So in order to convert this mile square into the feet square, we need to make it 1 mile. We know that 1 mile is 5,280 feet. So we need to just multiply 5,280 square with 7.03 miles square, and we need to divide this term into 7.839 multiplied by 10 to 7, and the answer of this solution is 0.4 feet or 4.8 inch. After this point, so we find RD, and we found RD. So what we need to use, we need to use our only formula, which is RD, depth of direct runoff, is equal to from M1 to the interval, total interval and the total of the rainfall event, which is our runoff, minus phi index delta t. Okay, so in order to do this one, let's move here. Okay, so let's start with when m the interval is 1. What happened when interval is 1? Let me bring back, wait. Okay, here is the table. Let me copy this table and then bring back here. Okay, so we know that when m is 1, we are gonna go through the top, the highest rainfall, which is 2.2. So in order to write here, oh sorry, sorry, in order to find this Rm, we just need to add this 2.2 and RD. We know that RD is 0.8, pardon, 4.8. So 2.2, sorry, 4.8, which is RD, is equal to 2.2, which is the highest rainfall here for M1, and minus phi index multiplied by delta t, which is 0.5 interval, because half an hour we are working, right? Here, when we make the calculation, we will have theta is minus 5.2 inch per hour as this. So the intensity, let's say, is minus 5.2, which is impossible because there is no when you see intensity is gonna be positive, right? There is no way to calculate. Minus is not going from soil or ground to the sky; is coming from sky to soil or ground. So that's why this, if you see this minus term in this phi index, it means it's impossible, and then we just neglect, and then we know that this for m is equal to 1 is incorrect. Okay, the next step is for m is equal to 2. For m is equal to 2, we need to choose two highest one, which is 2.2 and 2.08. Then we are gonna substitute these terms into our formula, which results in 4.8, 2.2 plus 2.8, make it straight, okay, 2.2 plus 2.8 minus phi index, 2 times of this phi index, and the interval is 0.5, so the 2 times interval, right? And when we solve this equation, our phi index is gonna come minus, again, minus 0.52 inch per hour. Again, that means for m is equal to 2 is impossible. So we need to jump. For m, the interval is gonna be 3. Let's go through. For m is equal to 3, then the highest one is 2.2, 2.8, and 1.33. So let's edit all this term, and as you see here, 2.2, 2.808 plus 1.33 minus phi index multiplied by 3, 0.5 interval. This one is given our phi index is equal to 0.54 inch per hour of phi index, and that means it's correct. It can be. Let's make it. Let's check it out. Okay. We need to multiply this phi with delta t, which is 0.54 multiplied by 0.5 hour is gonna give us 0.27 inch. Let's go to our table. Let's investigate it. Above 0.27, 1, 2, 3 intervals is seen. So that means this 0.27 m is equal to 3 is correct. If it is m is equal to 3 and then for this phi delta t number there are 3 numbers above this number, we have a correct calculation. Alright, when we have 0.27 we start to do Excel again. Let's go back to Excel. Okay, let's write it here. Excess runoff hydrograph. So we know that for excess runoff hydrograph we have 0.27 phi delta t, right? So we have these guys. Let's make it is equal to this guy rainfall minus 0.27. So 1.06 and 3 ones, right? 1.06, 1.93, 1.81. When we go through up, let's go up, or down, let's go up, you will see this is all minus, which is impossible. So we just delete it. So we have 1, 2, 3, 4, 5, 6, 7 events, but there's excess runoff, which means like there is an before it was going into the soil, then this in this period it start to get accumulated on the overland. Okay, so excess runoff hydrograph is 3 events. How we are gonna draw this one? Let me show the example of this guy. Okay, this is direct runoff hydrograph, the storm hydrograph, and then this is hydrograph or excess ERH. As you see here, we can see the precipitation begins. Let me bring this guy here. Let me take this. Okay, the precipitation begins at 8:30, then 9, 0.15 starts, then it goes to 0.26. Then here we have this excess the phi index, which is 0.27 inch per 1/2 hour, and below this one is called excess rainfall. Okay, this is how we see in hydraulically drawn excess runoff and direct runoff hydrograph. And we done our question here. If you have any question, just let me know. The second example is determine the runoff coefficient for the storm in example 1, the previous example. And in the case of calculation of runoff coefficient, we need to use this formula, which is C is equal to the runoff depth over the total of rainfall event. Okay, in this question, previous table we are using again. For the previous question, we know that RD, which is the depth of direct runoff, was 4.8 inch, right? Okay, let's see the rainfall. Let's write it here, rainfall from this table. rainfall was 0.15, 0.26, 1.33, 2.2, 2.08, 0.2, 0.09. Okay. In order to find this RM, we need to know all these terms, right? So RM is the total of after the excess rainfall begins or direct runoff begins, which is here after 9:30, right? So it's gonna start 1.33 here till down, because till here, so this two 0.15, 0.26 is gonna saturated soil. Then after that is gonna start to the direct runoff, or how can I say, surface water, surface flow, overflow, overland flow. So what happened here? Topla. Okay, I put extra parenthesis. Okay, 5.9 is our answer of our aim. So C, which is our runoff coefficient, is equal to RD over 5.9, which is 0.813599 is our runoff coefficient. So it's easy, it's very easy to calculate. Abstraction using infiltration equations. Do you guys remember from subsurface water we have infiltration equations, which is Green-Ampt equation, Horton's equation, and Phillips equation. There is a table for each cases for cumulative infiltration, infiltration rate, and cumulative infiltration at ponding, which is FB. All the formulation is given here in this table. We are gonna calculate the losses due to the infiltration. So we can calculate the surface water. In order to do the infiltration equation with interval or iterative procedure, we need to follow this flow chart. Let's go through and then let's investigate step by step what does it mean. Okay, let's consider we are at this stage, which time is equal to 0 and infiltration, cumulative infiltration is 0. So dry soil. Then we just follow here on the next step where time is t, okay, and the cumulative infiltration Ft is known, which is given first. We are just gonna calculate infiltration rate, which derivative of cumulative infiltration, right? And then we are gonna go through checking if the infiltration rate is smaller or higher than precipitation rate, so intensity of the rainfall here. If it is the infiltration rate is smaller than intensity, ponding occurs. Because intensity is high, the infiltration rate is low, so that means the water is gonna be on the surface, right? Because the water is not anymore infiltrate down and then it start to ponding over here, the surface of the ground. If infiltration rate is bigger than intensity, directly goes to no ponding. There is no ponding, okay? Then we need to jump another step, which is we are gonna add delta t on the time. So the time interval we are gonna add, we are gonna calculate the cumulative infiltration, and then after that we are gonna calculate the infiltration rate. which is, as you see here, the infiltration rate is I multiplied by delta T, because I is smaller than F, so we can just directly multiply the rate of infiltration, which is IT, multiply delta T plus FT, is gonna give us the cumulative infiltration in the next iterative values. Then we will just go down again, and then we will see if the infiltration is higher than intensity or lower than intensity. If it is lower than intensity, then ponding occurs again, okay, and then we follow up and then go back to up to see the iteration. If not, if infiltration rate still is infiltration rate bigger than intensity, there is no ponding occur again, then we will calculate T delta T is equal to Ft delta T, which is the prime is gonna go, and then we are gonna go to again the initial position. Then we will just add not T anymore, T plus delta T, and then we will start on this one, and then taking this Ft delta T as our initial condition. So this flow chart is showing us this procedure. Okay, let's go through another example. A rainfall hydrograph is given in columns 1 and 2 of table. If this rain falls on a sandy loam soil of initial effective saturation 40%, determine the excess rainfall hydrograph. We have, there is a time in given minute, and we have rainfall with the incremental with the centimeter. Let's go through and then try to solve this question. For this question, as you see there, here, let's see, is a sandy loam. So what we need to do, we have to find from our green amped infiltration parameters for various soil classes where it falls and what is these parameters. So it is, let me close this one, it is here, as here, as you see. Let me make it bigger. So we have eta, which is porosity, effective porosity, wetting front, soil suction head, psi, hydraulic conductivity, which is K, is given for sandy loam. And right now we are gonna calculate it, other parameters. In order to find change of moisture content on the soil, we have a formula by using, here, delta theta is equal to, let me put here, okay, delta theta is equal to 1 minus SE delta theta E. We know that we can use, let's write it here, is equal to 1 minus saturation of effective saturation is 40%, which is 0.4. Let's write here 0.4 multiplied by theta is which is effective porosity, which is 0.412. Okay, so delta theta, which is the change of moisture in the soil, is equal to 0.247. Okay, after we found this term, we can calculate it, the psi delta theta, which is equal to 0.247, which is delta theta, right? 247, and we need to multiply this term with what? With psi is 11.01. 11.01. This guy is then 2.72 centimeter. Where we are using this one, we are using this guy in order to find the infiltration rate as F is equal to hydraulic conductivity of the soil, parenthesis psi delta theta, right? Delta theta over the cumulative infiltration plus 1. So if this is T, so the cumulative infiltration is T. If it is T plus delta T, which is the incremental, let's say, so we are gonna write here the T plus delta T time of infiltration, cumulative infiltration. We need to substitute here, and then we will find our rate. After this point, let's go through the our Excel and write it down everything. So in order to find our time level, and then if we have rainfall incremental, how we are gonna define all the parameters and then find the excess rainfall hydrograph. Okay, let's write it down here. Time, which is in minute, right? And we have from 0 to 10, 20, so it's 10 minutes interval till 180. And after we do this time interval, let's go to rainfall. So this one incremental rainfall, let's say rainfall here. Okay, rainfall incremental. So it's given, which is at 0 is 0.18, then 0.21, 0.26, 0.32, 0.37, 0.43, 0.64, 1.14, 3.18, 1.65, 0.81, 0.52, 0.42, 0.36, 0.28, 0.24, 0.19, and 0.17 is the incremental rainfall. Okay, let's expand it. Okay, so if we want to calculate the cumulative rainfall, cumulative rainfall, which is also given centimeter, what we need to do is, here is 0, as we see. Here is we can say this one is equal to this guy plus previous one. So no, sorry, basically it is equal to this guy plus this guy, our previous one plus the incremental position is 0.18, and then when we scroll down, we are gonna have the, like, for example, if we want to calculate here, so this one plus this one, 0.37 plus 0.97, giving us 1.34 centimeter per centimeter of rainfall. is given, where I can I want to make it together. Let me see here. I can see here. No, I don't see. Maybe this one. Yeah. Okay. So it's for the rainfall, cumulative rainfall, we found it, and we are gonna find the intensity of the rain, which is centimeter per hour. How we are gonna calculate this one intensity? We are gonna make it like how much in the interval, okay? 0 point, like for example here is equal to the incremental rainfall over the time period. But here the time period of 10 minutes is gonna be like 10 minutes. We need to convert it to the hour in order to have the unit consistency. So 1 hour is 10 minutes is 0.167 hour. So when we divide it, we are gonna have for all the intensity at the last is 0, so we can just delete it. So we found that intensity as well, and that's it for the rainfall. We also like make it together. Okay, let me do it. Okay, rainfall, we have the rainfall. So from after that we need to calculate the infiltration. So infiltration, we need to use another formula in order to find like the infiltration. Let me write it here. Infiltration. So first of all, we need to find the infiltration rate, which is also centimeter per hour. So in order to find the infiltration rate, we need to use, as I previously showed. No, I didn't show. So let me bring back, write it down here. Okay, for our infiltration rate, I don't know where it's. Yeah, here. All right. So in order to calculate the infiltration rate, we need to multiply by the hydraulic conductivity, which is not here. Here. Hydraulic conductivity, which is 1.09, right? 1.09. Where is it? Here. Okay. So infiltration rate is equal to, so it's 0. There is no infiltration rate after 10 minutes it starts, let's say. Okay, so we will go one step ahead. 1.09, right, multiply by psi delta theta, which we found it 2.72 centimeter, 2.72 centimeters over the cumulative infiltration, which is 0.18 here in this case, plus 1. So 17.56111 is gonna given for in our case. Then let's scroll down and then find our infiltration rate. When we compare the infiltration rate and intensity, we will see there's differences. These guys, the infiltration rate is higher till this point, right? So as you see is 4 and 2, 3 and 2.5, 2.7, 3.83. Then we say after this point, let's say after this point, the ponding occurs, but we don't know where to where. So let's just highlight it here. Then we will, after this point, we need to calculate not like this guy, because right now the ponding occurs. So we need to calculate it in another way. Let's calculate our infiltration rate when ponding occurs. Okay, now we need to calculate the cumulative infiltration in order to find the rest of the infiltration rate, because here F is gonna change inside the cumulative infiltration, because here the whatever we get the rainfall is gonna be a infiltration, the cumulative infiltration. Let's see right now how we are gonna define our cumulative infiltration when the when the head up ponding occurs. I think here, yes, right. So if we need to use this nonlinear equation and use the this equation, and we are gonna find our infiltration, right? Cumulative infiltration when it's ponding. Okay, now we need to find the cumulative infiltration on this side in order to find later on the infiltration rate. So we need to find first of all cumulative infiltration. We are going to use this formula. Let's write it down here, which is equal to, let's say, okay, our initial guess. Let's first of all calculate it K delta T, K T, let's say, T, which is equal to 1.09 multiplied by 0.1167. Okay, and we are gonna because it's iterative procedure, we need to have initial guess of our infiltration. I choose again the same number, which is 0.182. okay, then right now let's try to calculate here. We are gonna start here is equal to, I'm saying, the first ft plus delta t, which is my initial guess, minus my previous cumulative infiltration, which is the previous one is 177 rainfall, cumulative rainfall, because whatever the rainfall comes, we were saying it goes inside the soil. So the cumulative rainfall is the cumulative infiltration, previous infiltration. Then minus, we know that phi delta theta, where is it? Phi delta theta, hold on. It is 2.72 phi delta theta multiply natural logarithm, make a parenthesis, another parenthesis, my further infiltration is my initial guess, plus phi delta theta is 2.72 parenthesis over, make another parenthesis, my previous cumulative infiltration is 172, well, 177 plus 272, 2.72, okay, double parenthesis, close, minus, so I will bring this K delta T over here, so I will make the right hand side 0. K delta T is this guy, so I need to make it constant, so I will put $sign in both sides, so it's gonna be constant. So when I do, this guy is minus 0.5, so I need to change this one. What I need to do is I need to bring here what if situation. So I need to see goal and seek parameters. So I click here and then I will bring, I say, okay, which one is gonna be the arrange one? Is this guy I will arrange to value of 0. So the right hand side is gonna be 0. And which one is gonna change? My initial guess, I want to change it. So I will find what is my cumulative infiltration when I do these parameters, okay? So when I run, this guy is 0 and 2.2 is my cumulative infiltration. So I will write here, let me copy this formula, sorry, copy this formula, then paste here, okay? So this guy is 2.2, I found it. So I will make another procedure here. So same thing I need to do, but I need to change everything again. So what is my R4? My R4 is my first, which is this guy, right? The initial guess. So my initial guess, let's modify this one, because right now we are gonna change it everything, because we will not take it out anymore. Rainfall in cumulative infiltration, we are gonna choose the previous one. So I will modify and then I will scroll down. Okay, how we are gonna do? We are gonna check R4, which is R4. Our first guess is again, let's say this guy, okay? So R4 is fine. R4 previous cumulative infiltration, I will change with this one. So instead of J13, I will choose this guy, which is N14 minus 272 natural logarithm R4, which is our initial guess, then 272, and again I need to change this one, my previous infiltration, which is this guy, and I will just run, okay? Then I will do again the what if section, what if function. So I will say, okay, I want this guy as 0 to approach 0, and change this guy and then give me the cumulative infiltration at this case. And then when it run, it show that it is 2.588, so it's almost 2.6. So let's write here 2.589. 2.589 is gonna be my cumulative infiltration. Then we need to do till here, and then we are gonna compare our cumulative infiltration. We will go through till down, and then we will compare. We will calculate the cumulative infiltration rate. Then we will compare with the rainfall intensity till where it's gonna stuck. Then we will compare, and then we will say, okay, ponding is stuck here, and the rest is gonna be not ponding anymore, no ponding. So let me write it down, and then I will calculate, and I will come back. Okay, I write down till here the cumulative infiltration by using this formula. So I change FT right now, the new cumulative infiltration, these guys. So I wrote it, and I modified the infiltration rate till here, as you see. And when I have 1.7, you see the right now here, sorry, 174, which is 167. The rain intensity is lower than infiltration rate. So I said, okay, then over here there is no ponding. So I will just okay, I will just delete this stuff. Where is it? Okay, right. So all right, okay. So just till here there is an ponding we need to calculate. Then after this one, the cumulative infiltration is we need to calculate as before. Okay, what we did previously. Then we are gonna calculate here. Then after that we are gonna add it here. I stop here again. I will calculate the rest. Then after that I will come over the excessive rain hydrograph. Now calculate excess rain fall. Excess excess rainfall, cumulative and cumulative excess rainfall. So how we are gonna calculate this one? We are gonna go to ponding. We will see the cumulative rainfall minus cumulative infiltration. So is 0.21 the first one. Then we will go through all the ponding places. So it's gonna be 596 when the time is 140 minutes. This is cumulative. We can find the incremental. So how can we find the incremental? So it's gonna be is equal to this guy, the last one, minus previous one. Previous one is 0 here, right? 0.21. Then we can see 0.96 minus 21 is 0.75. 3.78 minus 0.96, 2.81, and blah blah. This one is the incremental procedure of excess rainfall. So we can construct our incremental excess rainfall hydrograph, and we are done here. As you see, we construct our all variable, and then let's see how our graphical or figures can be seen. Okay, when we draw our hydrograph, as you see here, then rainfall and infiltration rate, we have potential rainfall, potential infiltration and rainfall. Okay, and as you see, here is the rainfall and here is the infiltration as well intercept. Here is the excess rainfall rate here, or rainfall hydrograph over here. So, and when we draw our cumulative rainfall and infiltration, as you see again, these guys is rainfall, and this is the potential infiltration. So the difference is our excess rainfall. So this is shown as graphical representation of our here all the information we draw. So this question is a little bit long, but it's better to understand like what is the excess rainfall and then how we are gonna calculate from our infiltration. It's gonna take it's time consuming, but uh, it's very useful to model or design the city drainage. All right.